Students, good morning. Today we are going to see Bayesian network in artificial intelligence. What is probability? It is a field closely related to statistics and deals with the possibilities of an event. And it is quantified as a number between 0 and 1. 1 means occurrence of event and 0 means non-occurrence of event. Chords example. Let us take the chords example. There are 52 chords in a deck, out of which 22 chords are in red color and 22 chords are in black color. Okay, so the probability of taking red and black chords, there is a 50-50 probability of taking red color chords and black color chords. So this means that there is an equal chance of taking red and also a black chords. Joint probability. What is joint probability? It's a measure of two events happening at the same time. See this diagram. From a deck of 52 cards, the joint probability of picking up a card that is both red and 6 is probability of 6 intersection of red equal to 2 by 52 equal to 1 by 26. That is equal chance. Since a deck of card has two red sixes, see the two red sixes. One is 6 of hearts and another one is 6 of diamonds. See the 6 of hearts and 6 of diamonds. And how many sixes are there? 4, right? The 4 sixes are there, out of which 2 sixes are in red color, that is 6 of diamond and 6 of heart. And there are 26 red color cards on the deck of cards. Okay. And because of this event, 6 and red are independent. In this example, you can also use the following formula to calculate the joint probability. So probability of 6 intersection of red equal to probability of 6 into probability of red equal to 4 by 52. 4 means how many sixes are there in the card? 4, right? 2 black color and 2 are in red color. So 4 by 52 into red. How many red color cards are there in the deck of cards? 26. So 26 divided by 2 equal to 1 by 26. So this symbol is referred as an intersection. And the probability of event x and event y happening is the same thing as the point where x and y intersect. Therefore, the joint probability is also called the intersection of two or more events. What are other probabilities? Marginal probability. What is marginal probability? It's a probability of an event irrespective of the outcome of another variable. And what is conditional probability? It is a probability of one event occurring in the presence of second event. The full joint probability distribution specifies the probability of values to random variables. Take the joint probability distribution of two random variables x and y. See the table x and y. If y is true and x is true, the probability value is 0.30, and y is true and x is not true, then the value is 0.22. Then not false, that is false. If y is false, x is true means the value is 0.60, and if both values are false means the value is 0.02. So if there are two variables, then the total number combination is 2 to the power of 2 equal to 2. And if there are 3 random variables, then the total number of combination is 2 to the power of 3 equal to 8. And if 4 variables, then the total number of combinations will be 2 to the power of 4 equal to 16. So if there are n number of variables, then the total number of combinations will be 2 to the power of n equal to n. Okay. So the number of variables increases, the combinations will also be rapidly increases. So drawback. What is the drawback of joint probability distribution? If the number of variables is more, then the total number of combinations is also more. And if the number of variables is more, then the time and space complexity also be a huge one. Then what is the solution to joint probability distribution? The solution to joint probability distribution is the Bayesian network, because the dependencies of any number of variables can be represented using graph, that is by nodes and edges. And Bayesian network is a data graph in which each node is variable and edges are relations. And these variables may be a discrete or continuous. The set of nodes is connected by links or arrows. If there is an arrow from node A to B, then node A is said to be parent of B. See the diagram. The arrow comes from node A to B, so A is a parent node. So each node X has a conditional probability distribution, probability of X, parent of X, that quantifies the effect of the parent of the node. Let us see some examples. 4 nodes are given: node A, B, C, node A, B, C, and D. And node A and B are What are the conditions? Node A and B are unconditional, independent, evidence and parent nodes. Okay, and if you take node C and D, they are conditional, dependent, hypothesis and child node. Then now we are drawing the Bayesian network for the above variables. A and B should be independent node, right? So they are in green color, and node C and node D are dependent. Okay, assume node C is dependent of A, so the RMS should come from node A to C, and assume the node D is dependent of both A and B. Okay, so the RMS come from A and D. Okay, so C and D are dependent variables and A and B are independent variables. Okay, so this is a Bayesian network for the above variables. And to see the conditional probability tables. See the table 1, the node A and B are independent nodes, so we can directly compute the possibilities, the probabilities. Probability of A is 0.3, probability of B is 0.6, and the probability of node C dependent on node A, right? So the value is 0.4. Next one, probability of node C not dependent of A means 0.2. And next one, probability of D dependent on both A and B means 0.4, and probability of D dependent on node A but not dependent on node B equal to 0.4. And next one, probability of D not dependent on A but based on B, that is dependent on B, is 0.2. And last one, probability of D not dependent on A and not dependent on B is 0.01. Now we separate all the values into different tables. Table 2, table 3, table 4, and table 2. Probability of A is 0.3, probability of B is 0.6. And if you see the table 3, compute the probability of C, node C. If A is true, the value is 0.4. And if A is false, the value is 0.2. And if you see the table 4, compute the probability of node D. And node A, if node A and B are both are true, the value is 0.7. A is true, B is false means 0.4. If A is false, B is true means 0.2, and if both are false means 0.01. And it's a formula to compute. Formula equal to probability of D dependent on A comma B into probability of C dependent on A into probability of B into probability of A. So this is a formula to compute the above probabilities. And next one, burglar algorithm, burglar alarm. The alarm will ring either if a burglar enters the home or an earthquake occurs. Okay, a house owner fits an alarm in his home. If the alarm, when the alarm will ring, either if the thieves enter into his home or earthquake occurs. And if alarm rings, the neighbors, person A and person B, has to call the house owner. Okay, so the alarm, either person A calls a house owner or person B calls a house owner. The probability of alarm rings due to burglary means 0.001, and probability of alarm rings due to earthquake means 0.002. The probability of alarm rings, burglary and earthquake, both are true. The probability for alarm ring is 9.5. If burglary is true, earthquake is false means then the probability of alarm will be ringing is 0.94. No burglary but earthquake occurs means 0.29. If both are false means the probability is 0.001. Okay, if alarm rings, the person the possibility of person A will call the house owner is 0.90, and if alarm is not ringing, the possibility of person A calls the house owner is 0.05. He won't, if alarm not ringing, he won't call. And person B, and if alarm rings, the person B will call the house owner, but the possibility of calling the house owner is only 0.7. Assume he is a little bit lazy. And if alarm is not ringing, the possibility for calling the house owner is 0.001. And it's a Bayesian network for the above example. Burglary and earthquake are independent variables. Okay, independent. Both are independent to each other. Okay, and alarm is dependent on burglary and earthquake. If earthquake occurs, alarm will ring. If earthquake not occurs, alarm will not ring, right? So alarm is dependent on earthquake and burglary. Person A, when the person A will call the house owner, only if the alarm rings, right? So person A and person B depend on alarm. So the person A and person B are dependent on the variable alarm, and alarm, the variable alarm is dependent on the variables burglary and earthquake, but burglary and earthquake are two independent variables. Okay, so this is a Bayesian network for the above example. So in the above example, the variables burglary and earthquake are independent. A variable alarm is dependent because depend on the variables burglary and earthquake. Person A and B, person B are dependent on the alarm. Thanks for watching this video.